let's talk a little bit about you have the drive system laid out in this vehicle. This is a pusher aircraft, so as I see the illustration of it, so you've got the engine in the back. So kind of describe for us how you have the drive system laid out.
It's a direct shaft, a direct drive to the propeller shaft from the aviation drive, which is two electric motors stacked on the same shaft.
Okay.
With our motor controller also, housed in the engine compartment, as well as the range extender generator, which is a 4-cylinder, 180 horsepower, turbocharged and boosted to over 250 horsepower gasoline engine.
Okay, now is this like a horizontally opposed type aircraft engine, or is it more like an automotive engine?
No, we selected for the range extender generator engine a personal watercraft engine.
Oh, okay.
For a number of reasons, primarily because I don't know if you've had a lot of experience on the lake in a personal watercraft.
Never.
But if you've ever seen their operating range, they really have two settings, idle and full out.
Full out, yeah.
And they're designed to carry a load constantly. And at 8,000 RPMs, with a direct shaft drive to the generator motor,
right.
They're designed to carry a load and overcome hydrodynamic resistance continually, and they're very reliable. How the high power to weight ratio, and believe me, we have looked high and low, literally combed, searched the world, all over the world for the optimal range extender generator engine.
Okay.
Automotive applications, motorcycle, superbike engines, horizontally opposed new diesels, microturbines,
right,
et cetera, et cetera. This, given all the factors that make the safest combination of electric motor, drive motor and range extender generator, is the optimal selection.
Right.
Ultimately, and by the way, you've probably already noted that this is a series hybrid design as opposed to a parallel hybrid design.
Right.
There was a lot of debate and a lot of engineering work that went into a parallel development path with parallel hybrid, series hybrid, and all electric. We selected a series hybrid approach because we believe, given all of the work and energy and brain power and resources being poured into the improvement of electrochemical and pure electron storage, energy storage technology,
yep.
In short, the evolution of batteries, we believe so strongly that the time is near that we'll be able to carry enough energy on board that we'll be able to swap out the range extender generator and its attendant 23-gallon fuel tank for lithium polymer and or supercapacitor batteries and battery management system in the relatively near future. So the engineering work that would have to go into completely changing a parallel hybrid design is substantial.
Yeah.
So to swap out a range extender generator for battery weight is just a lot easier for our customers. So, for example, when one of our aircraft owners comes back to us for an upgrade to an all-electric version, it's a lot easier for them, it's a lot easier for us.
Right. So let me see if I understand correctly. So what you've got is this aviation drive system is in the rear of the fuselage behind the passenger cabin, is that correct?
Correct. Firewall aft.
Okay, and the engine is this, I assume because it's coming out of a watercraft, it's probably liquid-cooled engine?
Correct.
Okay, so then you've got a radiator scoop someplace that's sucking air in and keeping the engine temperature down then.
Correct, with a heat exchanger.
Okay, well, we had lots of those anyway, P-51s and things of that nature, Spitfires, all of them running on that kind of a setup. So then from there, that goes into your what's the capacity of the generator?
The generator can put out over 220 up to 250 horsepower peak. Okay. So equivalent in kilowatts is more than enough to power the traction motor, which at optimal cruise speed of the aircraft pulls the equivalent of about 180 horsepower, okay, right? Including including electronics, heating and cooling of the cabin, et cetera, et cetera.
Right.
And with excess energy to recharge the batteries while in flight.
Okay, so then you've also got you've got what, AC induction motors that you're using then, a pair of those?
Correct.
Okay, and those are, I assume, go through a gearbox of some type, and then the shaft then back to the propeller.
Correct. As you're probably aware, propeller tip speed is critical in an aircraft. Right. I mean, the efficiency of the propeller is optimized at about 0.84, 0.85 Mach at the tip speed. So, the 2,700 to 2,760 RPMs is where our propeller shines. So, the gear reduction drive, is optimized from the traction motor.
Okay. So this gives it. Let's talk a little bit about what's the performance envelope you have for the vehicle, for the craft.
Best cruise speed, most efficient cruise speed is 160 knots, okay, which is a fairly fast airplane. Top end, VNE, as pilots call it, never exceed speed, is 310 knots, which is a little over 350 miles an hour.
Right.
So its install speed is 65 knots. So it has a wide performance envelope, and best cruise speed is a little bit faster than average Cessna or Piper or Beechcraft made aircraft.
So altitude, you're what, up to 18,000 or I don't assume you're doing a pressurized at this point.
No, the aircraft at this time, this model is not inflatable, or as we pressurized, as we call it.
Right.
So above 12,500 feet, for 30 minutes or more, the FAA requires supplemental oxygen on board.
Right.
Which is not a hard trick. Ultimately, we expect to pressurize the cabin, and certainly that'll be a standard feature in follow-on models. Not until 2013 or even late in 2013. Including the next generation aircraft, which we have on the drawing board now, and plugs and molds and such made for a 6-passenger twin engine pusher.
Oh, okay. Let me just see if I understand correctly. Did you design this aircraft from scratch, or was this an aircraft? I thought you implied that you'd actually bought the aircraft from an existing manufacturer at one time, and you're adapting it, or what?
Correct. We have designed a number of aircraft over the years, and about a year and a half ago, we realized that we're better off. We can put more resources into improving the aviation drive if we were to find an aircraft design that was already in production,
right,
but wasn't quite making it as a business. And unfortunately, there's a few of those out there in the U.S. general aviation industry. So many American aircraft manufacturers have been acquired and moved to China that there's a few out there to choose from. And we finally settled on an aircraft made by a manufacturer in Sebastian, Florida, and acquired the plugs, molds, fixtures, jigs, tooling, parts, et cetera, right, to make this aircraft under our brand and incorporate the aviation drive system. So now we own soup to nuts, the aircraft, the drive system, and we integrate them at the same factory.
Okay. And all that's located in Portland itself, or?
The aviation drive and controller technology and such, including all the way down to ESS, is made in Portland. The aircraft is made in Sebastian, Florida.
Okay. All right. You just kept that all down there then. All right.
Correct. I hope by the end of this calendar year, 2012, we'll be moving a substantial portion of our manufacturing out here to Oregon. There are a number of aircraft manufacturers out here in Oregon in particular that had done quite well, but just didn't make it. I mean, and ended up being either bought by a Chinese manufacturer or just going out of business entirely. Yeah. So there's a lot of talent. A lot has been invested in Oregon, and there's a lot of resources and capable engineers and employees here that we want to put back to work.